Hi all, welcome to another video of linear control system based on KTU syllabus, and today we are going to discuss the problems based on the polar plot. So the problem is the open loop transfer function of a unity feedback system is given by g of s is equal to 1 by s into 1 plus s into 1 plus 2s. Sketch the polar plot and determine the gain margin and phase margin. So by observing the function given, that is open loop transfer function, we know that the order of the system, order is, that is 3, s into 1 plus s into 1 plus 2s. So order is 3 and the type number is 1. So it is a type 1 order 3 system. So based on the basic rule for plotting the polar plot, we know that when it is a type 1 system, normally the polar plot will start from this side, that is from the minus 90 angle side, and it is an order 3 system. The polar plot will end in the second quadrant at 0. So we can draw the almost figure of the polar plot that we will get after sketching in the normal graph. So it is a type 1 system, so the polar plot will start from here and it will end at the second quadrant, and the approximate shape of the polar plot will be this. So we should obtain this graph. So by observing this graph, we know that the most of the portion of the polar graph is located on the second and third quadrant. So if we can arrange the x-axis and y-axis, that is real axis and the imaginary axis in the graph sheet, we can utilize maximum space of the system, that is the first and fourth quadrant. There is we can't see any part of the graph in the first and fourth quadrant. So we can eliminate that side and we can draw the second and third quadrant in the graph sheet. So this is the approximate graph we should get, and we are moving to the solution. So first, for sketching the polar plot, first we have to write the sinusoidal transfer function of the function. That is, by putting s equal to j omega, we will get the sinusoidal transfer function g of j omega is equal to 1 by j omega into 1 plus j omega into 1 plus j 2 omega. And here we know that we will plot the polar plot by varying the frequency from omega 0 to omega infinity. That we know. So actually we have to take number of frequencies and we have to check where are the points are located, like that. And the range of frequencies should be around the corner frequencies. So we know that here two first order terms are there, so two corner frequencies will be there, and the corner frequency of the term 1 plus j omega is, we know that it is corner frequency will be equal to 1 by t. 1 by t means it is actually it is the coefficient of j omega. So here for the first term the coefficient of j omega is 1. So 1 by 1, it is 1 radian per second, and for the second time the coefficient of j omega is 2. So 1 by 2, it is equal to 0.5. So 0.5 and 1 will be the corresponding corner frequencies that we can see here, and we have to take the frequencies around these values. And the next case is we have to find the corresponding magnitude and phase angle of the function. So we know that how to find the magnitude and phase angle. That is if we are first talking about the magnitude, we know that 1 by the magnitude of j omega is omega, that we know, and magnitude of 1 plus j omega, it is in the form of a plus jb. We know that the magnitude of a plus jb is root of a square plus b square, So likewise here we can write here a is 1 and the b is omega, so we know that root of 1 plus omega, so a square plus b square means 1 plus omega square, and here also 1 plus, for the term 1 plus j2 omega, the magnitude will be root of a square plus b square, that is root of 1 square plus 2 omega square, that is root of 1 plus 4 omega square. Okay, this is the magnitude, and if you are expanding the magnitude, that is mod g of j omega, that is by opening the brackets in the root square, we will get 1 by omega into, okay, by solving the terms, 1 by omega into root of 1 plus 5 omega square plus 4 omega raised to 4, that is 1 by omega into root of 1 plus 5 omega square plus 4 omega raised to 4. This is the magnitude. And if you are talking about the phase angle of the system, we know that there is no term in the numerator, so we can leave it, and in the denominator side the first term is j omega, so we know that the phase angle of j omega is minus 90 because it is in the denominator side, that's why it is minus, so minus 90. Then the second term, it is a first order term, and it is in the form of a plus jb. We know that the phase angle is tan inverse b by a, and we know that it is located in the denominator side, so phase angle will be minus tan inverse b by a. Okay, so likewise here we can write the tan inverse b by a, tan inverse omega minus tan inverse omega, and here also minus tan inverse 2 omega by 1, that is minus tan inverse 2 omega. Okay, so the magnitude will be this one and phase angle will be this one. Okay, and after that we have to draw the a table representing the magnitude and phase angle of the system for various values of frequency omega. Okay, here we have just take the values of omega from 0.35 to 1. Okay, we can take any values, that is if we are taking the value of omega around the corner frequencies, it will be better. Okay, so 0.35 to 1, here the corner frequencies are 0.5 to 1. Okay, so 0.35, 0.4, 0.5, 5, 0.6, 0.7, 1. Okay, so if we can if we take a large number of terms, okay, large number of omega values, so it is very easy to draw the polar plot. Okay, it will be more accurate, and for each value of omega we will find the mode g of j omega and the angle g of j omega using this equation. For finding the mode g of j omega, first we will substitute the value of omega is 0.35 in this equation, and we will get mode g of j omega. And if you are substituting the omega as 0.35 in this equation, we will get the angle g of j omega. Okay, and we have to find the phase angle and magnitude for different values of omega. Okay, actually the polar plot is drawn between the magnitude and phase angle of the system. Okay, as magnitude and phase angle as the axis, but normally in normal graph sheet we will draw the polar plot with the x-axis as real axis, real terms, and y-axis as imaginary terms. So we have to convert this form, that is it is in the polar form. Okay, in this polar form into corresponding Cartesian coordinates, that is rectangular form. Okay, that is real and imaginary terms. So we can do it in the calculator. Okay, polar to rectangular conversion we can use, and for each value of, that is for 2.22 is the magnitude and minus 144 as the angle, and we will get the corresponding rectangular coordinate as minus 1.78 and minus 1.29. So likewise we have to find the corresponding rectangular coordinates for each and every values of magnitude and phase angle for different values of omega. Okay, so this is the values we have to plot, and after that this is the actual polar graph. Okay, this is the polar graph. In the polar graph we will draw the polar plot. Okay, in the polar graph these circles represent the magnitude, and the lines, these corresponding lines represent our phase angle. Okay, but normally in this case today we are going to draw the polar plot in normal graph sheet. Okay, so this is the normal graph sheet, and in the normal graph sheet we know that the x-axis we will take it as the real axis, and the y-axis it is the imaginary axis. And at the starting of the problem I have already said that the polar plot will be on the second and third quadrant only. Okay, so we can eliminate the first and fourth quadrant. Okay, that's why with that we can maximum use the space of the graph. Okay, so here this is the real axis and this is the imaginary axis. So based on the table, okay, table values, we are taking the scales here, and we are plotting the points. Okay, each and every point we will plot, and after that by freehand just draw the polar plot. Okay, polar plot, and it should be end at 0 in the second quadrant. Okay, so this is the polar plot we will obtain. And after that, for obtaining the gain margin of the system, the gain margin of the system can be obtained by taking the inverse of the magnitude of our function, okay, our open loop transfer function at phase crossover frequency. Okay, so that is 1 by, actually the equation will be 1 by mod g of j omega at the phase crossover frequency. Okay, so here we can find that gain margin as we have to observe the crossing point of polar plot on the negative real axis. Okay, here the negative real axis is this one. Okay, so we have to find the crossing point of this polar plot on the negative real axis. So here it will cross the negative real axis at minus 0.7. Okay, minus 0.7. So our gain margin will be 1 by mod minus 0.7, which means 1 by 0.7. Okay, and we will obtain it as 1.4286 like that. Okay, so here you can see this 1.4286. This is the gain margin. Okay, and after that, for finding the phase margin, that is our gamma equation will be 180 plus 5gc, same equation as in the board plot. Okay, 180 plus 5gc. So for finding the phase margin, the first step we have to do is we have to draw a unity circle. Okay, that is combining the minus 1 value here and minus j 1.0 here. Okay, we can by taking it as the radius. Okay, that is 1 as the radius, we can draw a circle. Okay, using the compass. Okay, by placing the axis of the compass at 0. Okay, we can draw a unity circle. Okay, so for drawing this unity circle, the essential requirement is the scale should be uniform. Okay, so whatever may be the scale we are taking the x-axis, the same scale we should take in the y-axis. Okay, here in the x-axis we have taken that is 1 unit. Okay, 1 unit as minus 0.2. So here in the y-axis also we have to take 1 unit as minus 0.2 like that. Okay, so after drawing this unity circle, we have to check at what point the unity circle will meet our polar plot. Okay, so this is the point of meeting of this polar plot with the unit circle. Okay, and we have to draw a line from the origin which passing through the meeting point of polar plot with the unity circle. Okay, so this is the line. We have to draw this line from the origin. Okay, and after that we have to measure the angle from the positive real axis to the line we have drawn. Okay, that is from the positive real axis to the line we have drawn. Okay, we have to measure it in the clockwise direction. So we know that if you are measuring the angle in the clockwise direction, it will be negative value. So here we are taking we will get the value, the phase angle value as minus 168. Okay, so this will be the 5gc. Okay, this angle will be the 5gc. Here the 5gc is minus 168. You can use the protractor to measure the angle. Okay, here the angle is measured in the clockwise direction. That's why we are taking it as minus. Okay, negative. So 5gc will be minus 168. So we know that the gamma will be 180 plus 5gc. Here 5gc is minus 168. So 180 minus 168, which will be equal to 12 degree. So 12, you can see here. Okay, 12 degree is the corresponding phase margin. Okay, so gain margin is kg is 1.4286 and phase margin is gamma is equal to plus 12 degree. So here one thing you have to notice that if you are asked to find the gain margin in decibel, we have to take it as 20 log kg. That is 20 log 1.4286. Okay, using that equation we will get the gain margin in decibel. Okay, so that's all about this problem. I hope all of you understand the problem well. So thank you.